Okay, so we looked at different geometries with electron groups, but all of those electron groups were bonds. Okay, some of them were double, but they were all bonds. Some molecules have a lone pair, or more than one lone pair, on the central atom. And so then we have to describe the shape of that a little bit differently. So we actually talk about two different types of geometry, the electron geometry and the molecular geometry. The electron geometry is the arrangement of the electron groups. The molecular geometry is the arrangement of the atoms. Okay? If there are no lone pairs on that central atom, then they are the same. Okay? But electron geometry, we're looking at how are the electron groups arranged. Molecular geometry, we're looking at, well, what's the shape when we're just looking at the atoms? But we have to consider electron geometry when we're looking at molecular geometry. Okay, so let's look at ammonia. We need a Lewis structure. It's okay, I can draw that. Okay, so here's the Lewis structure for ammonia. We look at the central atom, we ask ourselves how many electron groups? 4. There's a lone pair and 3 single bonds. That's a total of 4 groups. 4 groups make a tetrahedron. Right? So here we've drawn the tetrahedron. That is the arrangement of the electrons, the electron groups. So the electron geometry is tetrahedral. The molecular geometry, we're only going to look at the atoms. So this is a lone pair, and a lone pair is repulsive. But electrons are very tiny compared to atoms. So if you think about what if we could actually see this, and we could see these atoms, those electrons would be so tiny that they'd be basically invisible, right? So what I like to do is I like to think of that as being invisible. So you find the electron geometry, and then to find the molecular geometry, you erase the lone pair. You make it invisible. You don't remove it. It's just invisible. So the balloons, we're not going to pop any balloons because then the rest of the balloons are going to spread out more. The shape that's left here we call a trigonal pyramid because it's not flat. That nitrogen is off the ground a little bit. So with my models here, here's a tetrahedron, and with a lone pair, that's like just taking the ball off the end. That stick is still there. It's repulsive to the other atoms. But what I've got left is not trigonal planar because it's not flat. It's a very shallow trigonal pyramid. Any questions? So you got to think about the lone pairs because they affect the shape. Those lone pairs, not only are they repulsive, they're actually more repulsive than the bonding pairs. And so they spread out more in space. And here's an illustration of that. So here would be a bonding pair of electrons between 2 nuclei. And they're kind of confined to this space. Here would be a lone pair on a nucleus. It's not confined on the other side by being close to this nucleus. And so it can just spread out. So this balloon would be more repulsive than that balloon. So this one at the top here is more repulsive than these guys. And so these hydrogens are like, ooh, we really hate that lone pair. I'm willing to get a little closer to these other hydrogens even though I don't like them either, right? Just to get a little further away. So what we observe for ammonia is that these angles are 107. They're squished a little bit together. I am not going to test you on the exact angle of ammonia. But I do want you to know that because of this lone pair, those guys are going to get squeezed together a little bit. And you should be able to tell me that this angle is less than 109.5. If we need to know exactly how much, we'll go look it up. but we need to know that the lone pairs are more repulsive and they're going to push the other atoms slightly together. Any questions? So let's look at what happens with 4 electron groups with lone pairs, now 2 lone pairs. So let's look at water. Water's an awesome molecule. So we draw the Lewis structure for water, and it ends up looking like this. We look at the Lewis structure and we ask ourselves how many how many electron groups on the central atom? 4. 4 things make a tetrahedron. Okay? So I've got a tetrahedron, and there's 4 points on the tetrahedron. 2 of them are going to be hydrogen atoms, and 2 of them are going to be lone pairs. So the electron geometry, the geometry of the electron groups, is a tetrahedron. To do the molecular geometry, I make these invisible. So we're just going to poof, invisible. And then we describe the shape of what's left. Come on. Having trouble. Yeah. So they came up with this super fancy name, bent. It's not linear, it's bent. I know you really like things like trigonal bipyramid. So here's our ball and stick model. 4 groups, tetrahedron, but now 2 of those groups don't have a ball on the end. They are lone pairs. So the sticks are still there. They're repelling these hydrogen atoms on the single bonds. But when we look at the geometry of the molecule, those are too tiny for us to see. And we look at the 2 hydrogens, and they form like a V, sort of, and it's just bent. The ideal geometry would be 109.5 degree angles, like this. Because there are 2 lone pairs here, and the lone pairs are more repulsive, that pushes these hydrogens together a little bit more, even more so than in ammonia. Ammonia was 107, here it's 104.5. But again, I'm just concerned with you knowing that, okay, the lone pairs are going to push them a little closer together. It's going to be less than 109.5. Okay? So we have repulsions between electron groups. We have lone pair to lone pair. That is the most repulsive. Lone pair to a bonding pair, that's sort of middle repulsiveness, and bonding pair to bonding pair is less repulsive. And so when we see these 3 related structures, no lone pairs, they're all going to be the same. Here, there's 1 lone pair up here. That has extra repulsion to these bonding pairs, and so the bonding pairs get squeezed together. Here, 2 lone pairs. The lone pairs repel each other more, and then they also repel the hydrogens more, so it gets squished. Questions? Okay, what about 5 electron groups? So let's look at sulfur tetrafluoride. So we do the Lewis structure, and it's sulfur, and we've got fluorines. And how many valence electrons? 4 times 7 is 28, right? And sulfur has 6, so 34. We've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. I have 2 more electrons I need to stick on there. What do? We put them on sulfur. We learned that sulfur is in period 3 and can expand its octet. So we'll just squeeze them in there. Look at the Lewis structure for this compound. I don't want to say it. How many electron groups? Well, the 4 bonds and the lone pair. 5 groups. 5 groups makes the trigonal bipyramid. But now one of them is a lone pair. The trigonal bipyramid had 2 different positions and the angles were different. So we could put the lone pair in the axial position or in the equatorial position. The angles are different. And it matters which position it's in. If the lone pair is up here with its extra repulsiveness, it's got 90-degree angles with 3 bonding pairs. If we put it in an axial position, it's got 120-degree angles with the other equatorial ones and 90 degrees with only 2 of these bonding pairs. It's got a little more space over here. So the lone pair goes where there's more space. So the tricky thing about this one is you have to choose to erase the correct piece, right? So here's my ball and stick model of the trigonal bipyramid. If I took one of the axial positions off, that's a different shape than if I take an equatorial position off. The other one was a triangular pyramid. This one is not. And again, you're really technical with this. It's a seesaw. You see? See how it saws? It's a seesaw. Seesaw. Okay? The lone pair goes in the equatorial position because that's where it has more space. Bromine trifluoride. So here's the Lewis structure because I'm tired of drawing Lewis structures. 5 groups again. 1, 2, 3, 4, 5. Trigonal bipyramid. 2 lone pairs. Well, where do you think the lone pairs go? Where there's more space. They go on the equatorial. So I'm going to take off 1, 2. Yeah, I had a seesaw, but then I took off one of those equatorial positions. Bless you. And now that's a T shape. Okay? The way they drew it here, it's a T on its side. You have to turn it a bit. So that's a T shape. Any questions? The way I remember this, there's this big chart in your book, but I just think about, well, okay, how many groups, right? So I know that 2 is linear, 3 is trigonal planar, 4 is tetrahedron, 5 is trigonal bipyramid, and 6 is octahedron. And then you look at lone pairs, and you make some of those groups invisible. This is the one where you have to be careful which one you're making invisible. You need to give the lone pairs more space than the bonding pairs. And then you describe the shape. Xenon difluoride. Just looking at this, you might say, oh, well, that's going to be linear, right? And this time, even if you guessed, you'd get it right, but not because you were thinking about it. Because if you look at water, you look at water, you would think that one's linear also, right? You're like, oh, well, yeah, that should be linear. We tend to overlook our lone pairs. Come on. What is wrong with you? There we go. Oh, well, those are just going to be in a line. But they're not. This one, what's happening is we have 5 groups, trigonal bipyramid, but we've got 3 lone pairs. And so the 3 lone pairs go around the equator where they have more space. And so the result is a linear molecule. She took her tutu off. She's got a leotard on underneath, it's okay. But this is the little girl in just the leotard. So with six groups, right? So BRF5. So there's 5 bonding pairs and a lone pair. 6 groups, that's this octahedron, right? All the angles are the same. So you put a lone pair on there, and there's a lone pair, and you make that invisible. I really want to make that one invisible because I don't like the imagery that I'm seeing now. Does that look a little weird to you? Yeah. People snickered when that slide came up. There, that's better. It doesn't matter because all the angles are the same. So on this one, let's take a green one off because it's easier to identify. That's a square pyramid, a pyramid with a square at the base, right? And if I took off one of the equatorial ones, it's still a square pyramid because all the angles are the same. It's just that the trigonal bipyramid one where it matters. So this is called a square pyramid. 2 lone pairs, xenon tetrafluoride. So here we've got 2 lone pairs, 6 groups total. So we've got this octahedral shape. We put 1 lone pair down here. The other lone pair now is going to go on the opposite side. We want the second lone pair over here because it's going to have more space that way. We don't want to have a lone pair 90-degree angles to another lone pair when we don't have to. So this is square planar. So this is a flat square. This one was a square pyramid, a square at the base, but it goes up to a point. Square planar. Here's that table. Now this could be helpful to you, and your book refers to, oh, we'll find the groups and then look at the table. Well, that's dumb. I'm not going to give you this table on an exam. Why not? Because you can remember this. This is not that bad. You've remembered much harder things than this. But it's there for you to check. So when you're doing the worksheet today, do it without looking at the table. Think about the balloons, count the electron groups, think about the balloons, see how many lone pairs there are, make those balloons invisible in your mind. And if you want to use these models and pull off things, that's fine, you can do that. Okay. Naming the shapes, yeah, there's some names you need to learn, but they are very descriptive of the thing. And so you should be able to remember those okay. So here's a summary of VSEPR theory. Geometry is determined by the number of electron groups on the central atom. We're not going to look at electron groups on the other atoms. The number of electron groups comes from the Lewis structure. So you got to have a Lewis structure. Electron group is a lone pair, a single bond, a double bond, a triple bond, or a single electron in a free radical. Each of those is just one group. The geometry depends on their repulsions, and the bond angles can vary because if you have multiple bonds, like a double or a triple, those are bulkier than a single bond, and then lone pairs are more repulsive than bonding pairs.